Hello, everyone. We're waiting for people to connect, and we will start in a while. I will be typing in chat, and you can also share anything you would like with us in the chat.
So we hope you're having a really nice afternoon. If you want to let us know from where you are joining us today in the chat, you can let us know, because we see a lot of apparently different nationalities and different countries being represented. So welcome everyone. And we are admitting participants, and the webinar will start in a few minutes.
All right, I think we can slowly start. Welcome everyone, and thank you for being here with us. I would like to pass the floor to Professor Dong, who will be the moderator today for this webinar.
Thank you, Kirariki. Welcome everyone, and thank you for joining us. So first of all, I would like to make a note that this meeting is being recorded for dissemination and documentation purposes. So yeah, if you have any objection, just let us know. So for this project, we are now running a project called LORELEI-X, which is a collaboration between the Cyprus Marine and Maritime Institute in Cyprus and NTNU in Norway and Technical University of Denmark, DTU. The aim is to advance the long-endurance autonomous marine technologies for search and rescue and environmental monitoring. So this aligns with the Cyprus smart specialization strategy, focusing on robots and zero-emission vessel design. So over the 3 years, our project will combine the technical innovation, such as the autonomous launch and recovery, dynamic modeling, cyber resilient navigation with capacity building and knowledge exchange. So we are working towards at least TRL number 5, proof of concept vessel capable of autonomously deploying the fleet of micro UUV and helping to elevate CMMI leadership in maritime and marine robotics. So part of this project, we are delivering this webinar. So today's webinar is about the innovations in vessel design and insight into unmanned surface vessel hydrodynamics, the challenge and the latest development. So we will cover 2 topics. The first one is advances in vessel maneuvering, modeling for the design. We will talk about the state-of-the-art maneuvering models, important hydrodynamic considerations, constructing theoretical maneuvering models, modular and economical approach for agile testing, and also extending the model to underwater vehicles. The second topic we are talking about is the vessel design fundamentals and challenges and innovation. We will look at different topics such as vessel design, current challenges, innovation and design, and also we look at the future direction. So in our webinar, we have 2 speakers. The first speaker is Mr. Nikos Patikidis. He has received an mechanical engineering in naval architecture and marine engineering from National Technical University of Athens, NTUA, and he is currently having a PhD degree at the Department of Marine Technology at NTNU. So his research focuses on marine hydrodynamics with particular emphasis on the hydrodynamics aspect of ship maneuvering. So he will cover the first topic of the webinar. And also the second speaker is Dr. Ashok Kumar. He is an assistant scientist at CMMI, Cyprus Marine and Maritime Institute, He's working in a Center for Naval Architecture, Ocean and Marine Engineering. He holds a PhD in Naval Architecture and Ocean Engineering from Indian Institute of Technology, Madras, IITM. His research focuses on ship design, hydrodynamics, propellers, opposite materials, and motion analysis of floating structures. Dr. Kumar has published extensively in reputed journals and conferences and has been recognized with several international awards for his research excellence. So let me welcome the first speaker, Mr. Nikos. The floor is yours.
Yes. So my presentation is going to be about how we can assess the maneuverability of a vessel and model it. And also I'm going to speak about how we can use this model in the design of unmanned surface vehicles. So I'm going to start by outlining a few typical methods that can be used to assess the maneuverability of a new design. Then I'm going to offer some details about how we can construct a modular mathematical maneuvering model. And I'm going to speak about two different models, one that relies heavily on model tests to calculate the parameters, and one that uses only theoretical modeling and approximate solutions and doesn't require model tests. Along the way, I will be highlighting the advantages and disadvantages of each method. And finally, I'm going to speak a bit about the need and usefulness of maneuvering models for designing advanced unmanned surface vehicles. First of all, why do we need to assess the maneuverability of a new vessel? Well, first of all, for safety reasons, it needs to be maneuverable enough so that it can avoid collisions and grounding, and it also needs to have survive in adverse weather, for example, where its maneuverability will be impaired further. It might need to navigate in ports and canals and generally in confined spaces. It might need to accomplish special operations like a special rescue vessel or a maintenance and supply vessel, which need to have advanced maneuverability capabilities. Maneuvering models are also used in course keeping to design automatic control systems and navigation systems, and they can also be used for unmanned surface vehicles to design, for example, the path planning algorithm for them. Now, the first option to assess the maneuverability of a vessel is to conduct model tests. Then we have to create a model, a scaled down version of the design, and conduct several tests in an ocean basin, for example, a turning circle or zigzag maneuvers. This option is deemed to be the highest accuracy option that we have, and for that reason, it's used also to validate the rest of the models we use. But it's not 100% accurate because it suffers from we do fruit scaling to use this method, so we cannot have the same Reynolds number between the model ship and the full scale ship. So things like the skin friction resistance, or for example, the locus of the separation on the hull might be different in the model ship than the full scale ship. So the track predicted might have some errors. It's also very expensive and time consuming. And in general, there don't exist a lot of ocean basins around the world. It's impossible to do a maneuvering test in a towing tank. Now, another method that has been gaining traction the last few years is conducting full CFD simulations, like a Reynolds-Navier-Stokes simulation. This has been made possible due to the advances in computing power. The programs that are frequently used are, for example, the STAR CCM or OpenFOAM and many others. It is generally very accurate because we can. It models all of the flow physics that are there in the problem, and except maybe turbulence, which is modeled, of course. It still remains, however, very computationally demanding because a very large amount of cells is needed, and it's a difficult problem to set up because, as we see here in this figure, we need a background mesh. We need to use generally the overset mesh methodology because we have a background mesh that is basically our basin, our ocean basin, and because the body will must be allowed to move freely within it, we need a body fitted mesh, a mesh that is following the hull around the domain. And to predict this motion, also we need to couple our fluid solver with a solid body motion solver. So the problem starts getting more and more expensive computationally and also complex to create all these meshes. We might need also a third mesh for the rudder, which is also moving relative to the hull. Now, the perhaps oldest method that is used to model maneuvering for ships is using modular maneuvering models, mainly because they require little computing power. In this case, we solve basically we solve the body's equations of motion in its degree of freedom, and the fluid forces are the external forces of the problem. During maneuvering, we don't need to consider all 6 degrees of freedom. Usually surge, sway, and yaw is enough as the ship moves in the horizontal plane on the free surface. We might need to consider a roll when we're dealing with a high-speed vessel, which will gain a large heel angle during its maneuver. Now, the coordinate system that we set up is fixed with respect to the ship, and its center of gravity is and its zero. The zero of the axis is usually at the center of gravity, and because it's moving with the ship, the coordinate system becomes non-inertial because it's accelerating and rotating as well. So to set up so we can write down the equations, which are basically like Newton's second law, mass times acceleration equals the fluid external forces. But we also have these extra terms that are Coriolis and centrifugal terms that arise because our coordinate system is not inertial. This U, V, and R here are the surge, sway, and yaw rate. And Fx, Fy, and Mz are the external forces due to the fluid. Now, these external forces, to calculate them, we first split them up into different modules. That is why it's called the modular maneuvering model. And I saw an outline of these modules here. So on the left-hand side of the equations, we have the inertia terms of the ship, which are easily calculated. It's just the mass and the moment of inertia. And on the right-hand side, the fluid forces are split into a module that is about hull loads that are proportional to acceleration. These are the well-known added mass terms. Then we have hull loads that are arise due to viscosity, like lifting forces and cross-flow separation forces. We might have hydrostatic terms. That's only if we consider the roll degree of freedom. We also need to model the loads on the rudder and the propeller, and wave loads if we are not in a calm sea as well. These modules are not modeled independently. We need to take into account certain interactions between them. For example, the hull will have a wake that will affect the propeller and the rudder. The propeller will have a slipstream. The rudder will be in the propeller's slipstream. And also the wave loads mainly act on the hull, but they have also an effect on the propulsion loads and the rudder loads. So I will first give the outline of a popular maneuvering model that is being used, that uses experiments a lot. It's called the Mathematical Maneuvering Group Model, or MMG model. And it's been in development in Japan across many years. So what we need to do, our main task is to calculate the fluid forces. The first step we can do is split those forces up into forces that are proportional to the accelerations and the rest of the forces. These terms are due to added mass forces. These are proportional to the acceleration, and mx, my, and zz are basically the added masses in surge, sway, and yaw. These can be calculated from potential flow, and we can use a boundary element program, for example, either 3D or 2D with strip theory. And these two other terms are, again, terms that arise because we are in a non-inertial coordinate system, and we get also fluid, Coriolis, and centrifugal forces. Now, for the added masses, they are generally affected by the presence of the free surface, and in a sea-keeping problem, for example, they are frequency dependent. But because the maneuvering motions are generally small, the accelerations are generally small, we can take their zero frequency values. Also, viscous effects do not really affect these added masses, so we can get their values from potential flow. Now, the rest of the forces that are left are split into hull loads, rudder loads, and propulsion loads. And we need to model each one separately. First, the hull loads. These are, I think it crashed. Yeah, I don't know why. So first, the hull loads. When we non-dimensionalize these loads, we can see that they only depend on two parameters. The first one is this V prime, which is the sway speed over the surge speed. And this is equivalent to the drift angle of the hull. And this R prime, which is the non-dimensional yaw rate. So since they depend only on two variables, this model does a Taylor expansion, a two-variable Taylor expansion of these loads to create these polynomials. We can see that it keeps terms only up to third order for the surge, for the sway and the yaw loads, and up to fourth order for the surge loads. And our task is basically then to determine these coefficients for these polynomials, and then we will have the hull loads for each state the ship can be in. These coefficients are known as hydrodynamic derivatives in the maneuvering community. We also need, in the surge, we have the ship's resistance, a term for the ship's resistance when it's moving in a straight line. But the longitudinal force will of course change when we have a sway speed and the yaw rate. Then the propeller loads are perhaps the easiest part to estimate. For this, we just use what is commonly done to calculate the thrust of a ship design. And we can use the propeller characteristics to get thrust coefficient, which is a function of the advance ratio. And then from that, we can estimate a thrust. And we can take the thrust and multiply it by correct for the thrust with the thrust deduction factor to get the surge force from the propeller. Now, the rudder loads are a bit trickier to estimate. We see this model uses these expressions. All three of these expressions are a function of this Fn. This is the normal force on the rudder. This force is calculated with this expression. This is the area of the rudder. UR is the total inflow on the rudder. This FA is like a lift coefficient on the rudder, and this will be determined experimentally. And this AR is the angle of attack on the rudder. To calculate this angle of attack, we need to do some trigonometry and see what is the angle of the inflow here relative to the rudder. And to estimate this vector, we need to estimate its components, the longitudinal and lateral part. The lateral part is easy in general. It's proportional to the sway speed and the yaw rate. And there is a correction coefficient. It's called the flow straightening coefficient because this lateral velocity is reduced a bit by the presence of the hull, because the hull straightens the flow as it is ahead of the rudder. The other component is quite harder to estimate because the rudder generally sits behind both the hull and the propeller, so it is in the hull's wake and inside the propeller slipstream. Now, after we obtain this force, we can project it with the appropriate cosines onto the ship's x and y axis. And we also see that in front we have some other corrections. These corrections account for some interactions between the hull and the rudder. This TR is called steering resistance deduction factor, and it's basically included because they have noticed that in model tests the resistance of the rudder, the longitudinal force, is a bit less than they expected. So it's not exactly known why this deduction is needed, but anyway, it can be estimated with the experiments. The flow behind the propeller is quite complex, so it might be associated with the fact that the flow is oblique when the vessel is maneuvering. Also, we have another effect. This A8 and X8 accounts for an effect called wing flap effect. Basically, when the hull and the rudder cooperate, when the rudder is deflected with an angle delta relative to the hull, some lift force develops on the rudder, but there is also some lift force that develops onto the hull. So we get some increase of the rudder loads. The total loads on the body will be different than if we consider the rudder alone, and will be larger. Now, this force acts here on the hull, so we need to account for it with this AH parameter, which is leads to about to a 30-40% increase of the rudder lateral force. And we also need to correct for where this force acts with this X8 parameter that corrects the moment arm so that we can calculate the moment. Now, to calculate all these parameters, we need to conduct a series of model tests. The first model tests are called rudder force tests in straight moving under various propeller loadings. In this case, the ship moves in a towing tank in a straight path, and different propeller loadings, propeller RPM, and different rudder angles are measured, and the force transducers measure the total loads on the body. From these tests, the rudder parameters are estimated. Then, to calculate the hydrodynamic derivatives, which are the coefficients on the polynomials we saw before, we need to conduct these two kinds of model tests. First is called an oblique towing test. In a towing tank, our vessel is being towed obliquely with a constant drift angle, and again, by measuring the total forces, we can determine the hydrodynamic derivatives that are dependent only on the drift angle, or on this V prime parameter. We don't have any yaw rate in this case. The second set of tests is conducted in this are called circular motion tests, and they require a special kind of facility, like the one you see in the second picture here. This is a circular, like a circular basin with this large arm, and here the vessel is being towed basically both with a constant drift angle and with a constant yaw rate. So these tests can give us the hydrodynamic derivatives that are both proportional to drift angle and yaw rate, the coupling terms, and also only proportional to the yaw rate. Now, after we have conducted these tests, to determine the parameters, we can basically get a plot like this, which is the total force, for example, here in the surge direction, with respect to the drift angle for various different yaw rates. Now, fitting our polynomials on these results, we obtain the hydrodynamic parameters. And we see here that the fittings are quite good, which is a sign that our terms capture enough of are accurate enough, and we don't need any more terms or something different. So after we have developed determined all of the parameters, we have our model, and we can use it to conduct with it several maneuvers, several tests. Our model is basically a system of 3 coupled nonlinear equations that can be solved, for example, using a Runge-Kutta fourth order method. They need to be solved numerically, but the solution process is very fast. It only takes a few seconds usually. Because of that, we can solve for many different types of maneuvers, many different initial conditions, revolutions, and other kinds of scenarios. Some results from this model are shown here, where you see the first is our 2 turning circles, left and right, and they are compared with model tests. And you see that the accuracy is generally quite good. And on the bottom, you see results from zigzag tests compared against experiments. Now, the drawback of this model is that it needs to use a lot of model tests, which, as I said before, are very costly and time-consuming. Also, if we'd like to change the geometry or some design parameter, we'd need to redo all these model tests, so that is not really possible. I will then show theoretical model that I'm also working on here that attempts to calculate all these different loads using instead a collection of theoretical methods, either analytical or numerical approximate methods, and doesn't need to conduct any experiments. So this was first developed by Professor Sodding from Hamburg, and it was later improved here at NTNU from Skiedzik and Faltinsen and Rablius and Christiansen. Many of the modules I described are the same between the two models. For example, the body inertia module, the added mass loads, propulsion, and hydrostatic modules are the same as in the MMG model, because anyway, these modules don't need any experiments to be determined. But the hull and the rudder modules need to be changed so that their estimation is purely theoretical. So for the hull loads first, the MMG model uses, as we saw before, these hydrodynamic derivatives, this Taylor expansion method. And but instead here, to calculate the loads theoretically, what is done first is to deconstruct the hull loads into potential flow lifting loads and loads that arise due to flow separation. So as for the first part, the potential flow lifting loads, if we see a ship from above and take a section of it, we can see it looks a lot like a hydrofoil. So the ship, we can think that the ship will act like a wing, but its span will be very small. Its span will be equal to its depth, basically. So it's like a very low aspect ratio wing. Because of this, usual popular methods like the lifting surface theory, for example, Prandtl's theory, does not apply in this case. And instead, we have to use a slender body theory, what's known as the slender body theory. This is a very popular method to, for example, assess directional stability for ships. It has those certain assumptions. The most important is that the ship is in potential flow. Also, it's accurate for relatively small drift angles and yaw rates, and that our body is slender, which a ship generally is. This assumption leads to the result that the fluid velocity in the longitudinal direction is not disturbed much. So we can, by doing some manipulations, we can deconstruct the problem from a 3D problem to a 2D problem for each cross section. And fortunately, we can do some analytical calculations, and then the lateral loads on each cross section can be related to the added mass, to the sway added mass of that cross section, and specifically the change of that added mass in the longitudinal direction. So this is not a hard method to use. We can relatively easily obtain these lifting loads. Now, as you see here, this is a RANS simulation, CFD simulation for a ship that is moving with a drift angle. And you see here that especially in the after body part, the close and especially close to the stern, we have a lot of flow separation. This is vorticity. These are vorticity contours along many cross sections, and we see here how large vortices are created. These vortices interact with the surface of the body, and they basically cause a low pressure region on the side of the body that significantly affects the lateral loads. So this effect is not taken into account from slender body theory, because I said it assumes potential flow. So we need to correct for it somehow. One way to correct for it is to use this what's known as the cross flow principle. basically for each cross-section, we assume that each cross-section is in a steady lateral flow, and the magnitude of this flow is basically the lateral velocity of the fluid at this section. It can be estimated like that. From this, so we can split the problem from a 3D problem to a 2D problem again for each cross section, and by either simulations or experiments for this 2D problem in steady flow, we can get a drag coefficient for every cross section. If we don't want to do all the simulations and experiments, we can get values approximately from the literature for shapes that look like our cross sections. For example, there exist drag coefficients for rounded rectangles, which would fit nicely the middle part of the ship, and there exist a few also for ship sections. This drag coefficient that we obtained with this method needs to be corrected because it needs to be corrected for the presence of a free surface, because it will be different with the free surface present. We need to also consider if the regime is laminar or turbulent. The values can be very different if the regime is laminar or turbulent, and also this deconstruction into a 3D from a 3D to a 2D problem for the cross sections is not really valid close to the bow and the stern of the ship, where the flow is quite three-dimensional. So we need to do some corrections for that as well. But after we've estimated the drag coefficient for each cross section, we can obtain the viscous part of the loads and basically for each section, and then integrate them along the length of the ship to obtain the total lateral force and yaw moment. The disadvantage of this method is that the potential lifting loads and these viscous loads are modeled separately, so their interactions are not taken into account. They are simply these two components are simply added up, whereas in a CFD simulation, of course, their interaction is taken into account. Now the rudder loads are shown here, how this module is changed to not need experiments. The expressions used are these. To calculate the longitudinal and lateral force on the rudder, we need first to estimate a lift coefficient and a drag coefficient. This is like what's normally done for a wing. And then these forces are projected, of course, onto the longitudinal and lateral axis of the ship. This beta r is simply the angle that we use to project. It's basically the angle of the inflow to the rudder relative to the x-axis of the ship. This A, alpha, is the angle of attack on the rudder, and we can get that by subtracting the deflection angle of the rudder, delta, minus the beta r. So to estimate the lift first, to estimate the lift and drag coefficients, to estimate the lift and the drag, we need a lift coefficient and a drag coefficient. These we can use, for example, these expressions. These are expressions for a rectangular finite aspect ratio wing. They are empirical formulas that, however, work quite well. They fit quite well with experiments. And so we can obtain the lift coefficient as a function of the angle of attack, and lambda, which is the aspect ratio of our rudder. If we have a different kind of rudder, we can change these expressions and use something else. Now, we need, as before, to account for some interactions between the hull and the rudder. One interaction is, if we see here, this is our rudder. Right above it, we have the hull's bottom, either the hull's bottom or the free surface in very close proximity. This will cause a blockage in the flow from the upper side of the hull, which is the same effect as the winglets that are at the tips of aircraft wings, for example. So this will cause an increase in the lift coefficient, and we can account for that. We can use this figure, and where an effective aspect ratio is given with respect to the geometrical aspect ratio as a function of the gap, the size of the gap. We see that the effective aspect ratio becomes larger due to this effect than it would be without it, leading to a larger lift coefficient. We also need to correct for the wing flap effect as before. Now, this is a bit hard to model, but Professor Sodding, who created this model, did a simplified simulation. He basically used two concurrent flat plates, one having the size of the hull and one having the size of the rudder. And he estimated these AH and delta XL parameters, which correct for this effect based on the size of this gap. So it's like an approximate method to correct for this effect. We can just use these two simple formulas which he used to fit the results with. Now, to obtain, we need to obtain two more things. We need to obtain the angle of attack first, and also the velocity, the inflow velocity to the rudder. Now, to do that, we need to calculate the two components of the inflow, the lateral and longitudinal component of it. The lateral component is generally easy to obtain. It's a function of the sway speed and the yaw rate of the hull. The longitudinal component is a bit harder. This is because the rudder generally or always sits behind the hull. So it is into its wake, and also it is partly into the propeller slipstream. You can see in this figure, for example, how you can see qualitatively the extent of the slipstream behind the propeller and how the rudder will be affected by it. To correct for the presence of the hull wake, we can simply apply a reduction into its velocity, and we can use the wake fraction for it and multiply the inflow by 1 minus the wake fraction to get a mean correction, a mean reduction of the inflow. Now, the propeller slipstream, the flow inside the slipstream is increased a lot relative to outside. And we see also that the shape of the slipstream is it changes relative to the distance from the propeller. Its radius reduces as we move away from the propeller, and eventually it gets a constant value far away from it. So we need to estimate both the velocity inside the slipstream, the fluid velocity inside the slipstream, and also the extent of the slipstream, its radius. Now we can do that easily for this position, a position far away from the propeller, simply by using the law of conservation of momentum, and which will then give these two simple formulas. But unfortunately, the rudder doesn't sit far behind the propeller. So again, luckily, Sodding did some simplified numerical simulations with a vortex tube, which is a way to model the propeller. And he computed values for this, the extent of the slipstream and the speed inside it based on the distance from the propeller. So we can just use these simple formulas again to obtain the values of to correct the values of the inflow to the rudder. Now, again, as before, after we've calculated all these modules and obtained all the parameters, we can solve the equations using a numerical method and obtain results for various maneuvers. For example, here I saw a result for a turning circle compared with experiments with model tests, and you see the accuracy is quite good. Here on the right, this is a turning circle as well, but it doesn't look like it because there's waves. There's waves coming from the bottom and moving upward here, and the waves cause a drifting of the ship towards the general direction of the waves. These are also compared with experiments. The dark dots are experiments, and the ship shapes are the results from the simulation. Now, the advantages of modular maneuvering models, firstly, are that by using them or creating them, we gain valuable insight into the physical phenomena that affect maneuvering, which is important if we are doing the design and we want to decide about which parameters we need to change to improve the maneuverability, for example. Especially with the second model, a geometrical feature can be easily changed, and the impact of these changes tested easily. Also, once the parameters are calculated, we can run many different tests, many different scenarios, because each simulation takes only a few seconds. So yes, that is not possible when we do model tests or CFD, because the cost of its simulation is too large. We can also very easily add different modules. Like, for example, if we have waves, as we saw before, or wind and current, different modules can be added, and the model can be changed and adapted for them quite easily. And the effect of, for example, having different kinds of waves, different amplitudes, frequencies, headings, all these simulations, we can run many different simulations with all these many different parameters quite fast with a modular maneuvering model. Also, after we have created the model, we basically obtain the dynamics equations of the body. We obtain a model of the body that can be used for other reasons. For example, for designing the control system, the control system of the vessel, or for example, the path planning algorithm for it. Now, the main disadvantage is, of course, that their accuracy is reduced relative to the model tests or CSD, and they might require some a bit more expertise in hydrodynamics to set up correctly, but CFD or doing model tests is also not very easy. And if, like the first model, we need to use experiments to calculate the parameters for it, then they can still be quite costly. Now I will talk a bit about how these models can be utilized in the design of an unmanned surface vehicle. So over the past few years, there's been massive interest also in the maneuvering community towards the design of unmanned surface vessels. This is because they are generally an inevitable development in the marine field. To achieve a mission, the USV needs to have definitely an accurate and comprehensive path planning algorithm that optimizes for something. For example, optimizes for the time the ship spends underway, and also a well-tuned and robust control system so that it actually can manage to follow the path that it has chosen. Now, maneuvering models are already being used to design, for example, course-keeping control systems. And they can also be very useful in the design of path planning algorithms. For example, a path planning algorithm definitely needs to find a path that avoids obstacles with enough clearance and minimizes the time spent underway. But it also needs to take into account the certain maneuvering constraints. For example, a ship cannot have a very large yaw rate. It needs to take into account the abilities of the ship, because if it doesn't, it might choose a path that the ship cannot possibly follow. So if these constraints are not taken into account, then the path chosen by the algorithm versus the path that is actually being followed by the ship might be completely different, especially when there's adverse weather conditions like large waves, wind, and current. I will show here an example of this to prove that this is the case. In this case, a path planning algorithm was designed for an unmanned surface vehicle that firstly it had the constraint that it needed to avoid obstacles and to minimize the time for the trip. This is an example of its application. Here, the vessel is assumed to start from this red point, and it needs to navigate towards this blue point, avoiding these obstacles, like these islands. So the first algorithm used chose this green path. Then a simple constraint was added that tries to take into account the maneuvering abilities of the ship, specifically that the yaw rate of the ship will be limited. This can be shown here, for example, when we have this vessel moving forward here and the yaw rate is limited, it can only follow paths that are within this clear region, and it could not possibly maneuver to this region that is crossed out. So this immediately reduces the available options for the paths that the algorithm will find. So applying this algorithm again with this constraint, a totally different path was found by the algorithm. So you see that the difference that having or not a maneuvering constraint on the algorithm makes on the chosen path. This is further illustrated in this example, where they conducted actually full-scale model tests for an unmanned surface vehicle, and they used again these two variants of the path planning algorithm to find two different paths. So the vessel needs to start from this red point and navigate towards this green point. And using the first algorithm that doesn't take into account the maneuvering abilities of the ship, this pink path was found. And then the constrained algorithm finds this blue path. And then they made the ship to try to follow each one of these paths. When you try to follow this pink path, you can see that it didn't manage very well, because in the beginning, the ship had a starting velocity towards the left. So to follow this pink path, it needs to do a very sharp turn to have a very high yaw rate, which is constrained. So you see here it overshoots a bit and cannot follow well on this path. But it managed to follow the constrained path much better, as you see here in this second figure. Yeah, that's all. Thank you for your attention. And if you have any questions, please ask them in the chat.
Thank you, Nikos. Do we have any question from the audience? Since now I don't see anyone typing questions on the chat, so the problem is that we cannot turn on, you cannot turn on your camera and your microphone, so that's why you need to type the question in the chat. Okay, but in this case, so I think we can proceed with the second speaker. But in the meantime, you still can ask the question on the chat. So please welcome the second speaker, Dr. Ashok Kumar. He will give the talk about the vessel design fundamentals, challenges, and innovations. Please, Ashok, the floor is yours.
Thank you, Dom. Yeah, first of all, thanks for the Lorelei project management team for organizing this workshop, and thank you, Dom and Nikos, for being in this workshop. So, as I've given introduction about me, I need not give it again. So I start directly from the topic. So today we shall delve into some interesting aspects in the naval architecture fundamentals related to the unmanned surface vessels. I've kept this presentation totally in a very fundamental level so that the audience from various backgrounds could understand the topic and understand the basics of vessel design and the fundamentals that are associated with that. So I have kept the topic of this presentation as challenges and innovations in vessel design, especially for the USVs. I have segregated this presentation into these following sections. The first section would discuss about some of the histories and fundamentals of evolution of ship design process, and then more specifically about the planing hulls. We will look at the resistance and predictions processes. And next, we shall discuss some fundamental aspects of the hydrodynamics that are associated with the planing hulls. Then we would discuss some of the specific design challenges that we encounter when we are designing these USV vessels. And then we would also discuss some of the advanced materials that are used for the USV constructions and the importance of the modular design hull forms. And fourth, I have kept as it's also important to discuss the propulsion concepts that are novel compared to the traditional ones, which could really aid the USV to achieve their missions. So that's also a part of today's topic. And finally, we shall conclude by briefly discussing some of the future trends and aspects where we can take aid of the AI in the design process. So this is a brief overview of today's presentation. So let's start a bit with the background on how the hull forms have been evolved over the time. So I've put two pictures, one from much older times and one a new yacht. So you could really see from the picture itself that how the transformations of the hull forms have occurred over these years and decades and centuries. So originally, the hulls were what we call displacement hulls. These were built since ancient time, and mainly they are designed for cargo carrying, stability, and efficiency. They move through the waters rather than on top of it. So they always occupy more volumes than just skimming over the surface, which made them steady, but they are not very speed. As technologies advances, the designers started developing semi-planing and the planing hull forms, which are quite modern and very economical as well in terms of speed efficiencies. These designs lift more the boat out of the water, and they also provide the high speed, as I said. So which means less in drag and faster in performance. So the today's hull take this even further. Modern boats are all about optimizing hydrodynamics using these advanced shapes. You have a lot of shapes that are evolving in every day, and there are high-tech materials, smart materials that are being used in the maritime industry to get the best out of the possible to get higher speeds, fuel efficiency, and endurance. So in short, the boat hull designs have come a long way. So from slow, steady to sleek and high performance. So this would be a brief intro to the first section of what we are going to have today. So let's segregate the hull forms into three types in terms of fruit numbers. So the first one would be the displacement hulls. If you see the graph, the y-axis would be the resistance and the x would be the fruit numbers. So if you want to classify the hulls in terms of fruit number, we do it as fruit numbers within 0.5 and fruit numbers between 0.5 to 1 and fruit numbers that are greater than 1. So the ships which are in displacement forms occupy the first part, which is less than the fruit number, which is less than 0.5, which are called displacement hulls. So these hulls maintain stability by displacing an amount of water equal to their own weight. So they are mainly designed for carrying high volume cargoes, and they are not for high speed applications. And the second one is something in between, which is 0.5 to 1, which are called semi-displacement. These could be generally medium speed hulls, where these hulls are generally used in ferries and more specifically naval applications such as frigates. So they do have, they do also follow the same path of displacement hull forms, but they are a little bit of speeder than the displacement hull forms. And the third one is the high-speed planing hull forms. They are designed purely for speed and agility. As they accelerate, they rise and skim over the water surface, and drastically they reduce the drag. These hulls have very limited internal volumes. They are not like the displacement hull forms, and they are commonly used for recreational purposes, boat sports purpose, high-speed missions, search and rescue, defense, surveillance, marine protected areas. These are some of the common applications of these hull forms. And so planing hulls are designed in quite different than the traditional hull forms. So I have just depicted the different underwater hull shapes of the planing hull forms. You have basically a 6 different underwater shape, starting from the round bottom, and you have a small chine, a V-type hull form. I can point out here. So this is a deep V type, which has a soft chine. So this increases some of the spray characteristics of the vessel. And this is a soft chine flat bottom because it increases a little bit of volume at the bottom. And it also has a very soft chine. The bridge is very soft here. So this is one of the kind of chine here. And it has a multiple chine here. If you see the fourth one on your bottom left. So it has a very much hard chains in multiple areas. So this is also a one typical hull form. And if you want to have a larger area in the deck space, so you would have to go for this hard chain shallow V, which is typically on the workboat kind of vessels. And there is also one more kind, which is hard chain of deep V sections. So these are the different characteristics of hull forms of the planing hulls, which are typically available in the market. Okay, so now let's go into a little bit of history. So we'll see how these planing hulls have been evolved over these years. So in 1870 to 1910, so the William Fruit begins studying this hydrodynamics of the planing surface through towing tank tests. I hope those who are in the background of naval architecture and hydrodynamics will definitely know who is William Fruit. So he's generally called as father of hydrodynamics. So he initially started this investigation on different hull forms, performance predictions, basically using the towing tank. And in 1898, Commodore Ralph builds the first documented training sailboat, which has a speed of over the twice the hull speeds. And in early 1900s, IC engines gains popularity and they are coming into the commercial usage, and that's come into play in vessel design aspects. So That was the first phase where we actually go into very high speed planing hulls. And between 1920 and 1930, and between this time, the World War I also has an influence in designing military boats for the World War things. So there were also some of the influence of the military aspects. And in 1920s and 1930s, Goodwar, Chris Smith. So these two gentlemen created a racing and recreational planning boats. Early influences of the military have also been included in this boat designs. And in 1940s, there is a serious need for small crafts in naval applications that drives further development, with designs evolving to integrate the speed and seakeeping, because people started using the planing hulls not only in the coastal waters, they also started going into much deep sea applications. So post World War II, the US Navy's Davidson Laboratory conducted very extensive experiments from 1960 until 2000, where they developed a lot of theories, experimental studies on the planing hull, published numerous technical literatures, reports from 1947. And the breakthrough point has come in 1964, where Daniel Savitsky published a very landmark paper, which is called Hydrodynamic Design of Planing Hulls, which introduced more reliable method to predict the resistance, basically resistance, trim, lift characteristics, dynamic lift for hard shine planing hulls. This was a very remarkable paper, and this is actually a fundamental paper for all those who kickstart in predicting the planing hull resistance. And fiberglass and aluminum constructions enabled mass productions of the planing hull and motorboats, pleasure crafts, and military interceptors. So these were something that happened in these years. And the deep hull forms were introduced in the late 50s, and they are still available in the market. And since 2000, the computational fluid dynamics are replacing the experimental towing tank test. So we are getting a lot of new propeller designs, novel propulsion systems such as surface piercing propellers. There are advanced hull forms like stepped hull forms, tunnels, catamarans, trimarans. So there are a lot of improvements in the hull designs, propulsion performances. So these are coming slowly into the market. And in late 2000 also, we have the advanced materials that are capturing the maritime industry, like carbon fiber, glass fibers, Kevlar fibers, which allow tighter and stronger hulls. So the access to the CFDs are becoming slow easy, because we have now a lot of open source results, open source models. What one of those was discussed in the previous session by the previous speaker. So, and recently we also have this AI-based optimization, where this additive manufacturing, virtual reality models, and the solutions, unmanned operations, autonomous systems. So these are the latest development that is happening in last a couple of years, or since 2020. So these are the evolutions in the design characteristics of this hull form. So if you see the planing hull form, I don't want to go into much detail, but I would like to briefly give how these operate. So generally the planing hull forms are typically behave as a displacement hull forms when they are operating at a very low speed conditions. But once the speed fruit number reaches greater than 1, they actually produce dynamic lift. So that is being depicted here. So this is the sea water level, and this dynamic lift is being produced at the bows area of the vessel, and where the buoyancy force is no more responsible for the craft. So the lift force is the major responsible for maintaining the stability of the vessel. So that is the beauty of this planing hulls. And so when you want to predict the hydrodynamics of the planing hulls, you need to understand there are different applications of that. So Jean Baptiste was a French mathematician. You can see him in the photo here. So who proposed that any body that is fully submerged in an ideal fluid will not experience any force. So if you have seen this D'Alembert's principle, which is most commonly known for this hydrodynamics prediction. So this is an D'Alembert's paradox. So whenever the body is completely submerged, and if the body is in inviscid or ideal fluid, so the body will not experience any force, and the pressure will be acting equal and opposite. So this is a D'Alembert's paradox, and this is only applicable when the fluid is ideal. But in real conditions, the fluid is not ideal, it has viscosity. So there will be pressure forces for any body that is completely submerged. So when you apply this concept in predicting the hydrodynamics of the planing hulls, you need to, the planing hulls are actually not a underwater phenomena, they are surface phenomena. So what you have to do is you have to see how the pressures are being distributed on the planing hull. So due to the surface distribution, there is a pressure difference that exists, that is because of the gravity phenomena. So any body that is on the surface of the water will experience a disturbance, and that disturbance will create a pressure difference, and that is why you have the pressure resistance. And because the water has to maintain its pressure equal to the atmospheric pressure. So that is why the water gets displaced and it gets modified, and it once it settles, it reaches the atmospheric pressure. So what happens is, if you see a body that is completely submerged, it will experiences only a pressure force. There is no wave phenomena underwater. And if the body is above water, there is no, what happens here is not the full body is having the wetted surface. So it will, those parts of the bodies which are underwater will only experience just the pressure difference. So here the worst scenario is a body that is close to the surface of the water and this is fully submerged. So this is a very, very extreme condition where the pressure is both hydrodynamics and hydrostatic. So this is a very important phenomena in predicting the hydrodynamics of any vessel, but this doesn't applicable for the hydrodynamics of the planing hulls. But there are some applications of the planing hulls where we deploy some underwater robots. So at those conditions, you need to consider this aspects. So, and when you disintegrate the total resistance that is acting on the hull form, it is basically frictional resistance, which has the viscosity as a component. And there are residual resistance. And the residual resistance is divided into wave resistance, pressure resistance, viscous pressure resistance. And since you are dealing with the high-speed planing hulls, you have the spray resistance. And there are a lot of appendages now being used in the planing hull form, such as interceptors, trim tabs, stern flaps, hull vanes, in order to gain more efficiency, also to stabilize the dynamic trim. So these are appendages that are attached to the hull form in order to energy saving devices. These are basically called as energy saving devices. And you of course have superstructure. So you have the air resistance as well. So these are the different components of resistance that will act on the planing hull form. Unfortunately, fortunately, we will not have the wave breaking resistance, because we don't have the phenomena of wave breaking occurring in the front of water. But what we really will have is a wave making resistance, which accounts for more than 80% of the hull form resistance, because I'll show you in the next slide. It's Lord Kelvin who initially discovered formally about the wave patterns that are generally created from a pressure point. So what he described was, when a pressure point travels on the surface of the water, it generates a wave behind it, and which is divided into a transverse and a divergent wave. So what you see here is a transverse wave, and what you see in the side is a divergent wave. So these are divergent waves that are moving away from the ship, and you see patterns of the transverse wave that are going in this direction. So that's why I've kept two figures. Maybe this is one from the high-speed hulls, which is very, very violent. This is a very small or low moving hull, so you will not be able to see this wave, transverse wave. So whenever, so consider the pressure points. So if you see in the hull form design. So the point at which the water surface intersect with the hull form in the beginning of the hull bow, which we call forward perpendicular. So that is act as a stagnation pressure, and at that point you will have high pressure and zero velocity. So as the length as you go along the length of the vessel, the pressure keeps on reducing, and the velocity will keep on increasing, and towards the middle of the boat you will not find any pressure, but you will have high velocity, and this will again rise towards the end of the boat because there is again a stagnation pressure at the end of your boat. So these are two discontinuities we have on the surface of the water. So because of this, the waves are being generated. So this is a basic fundamental of wave generation. And as I said, like for the planing hulls, which operates on the higher side of the fruit numbers, so they account for more wave resistance than the frictional resistance because they generate larger waves. So the energy that is being spent in generating waves is more than the conventional or cargo vessels. So the wave making resistance is more on the planing hulls than the other hull forms. So contribution of this wave making resistance for high speed flow numbers. So if you see that as the fruit number increases, so you will actually see that the total component of resistance, very particularly the wave resistance, is keep on increasing, and it decreases as the time. You can also see the components of the transverse waves as well as the divergent waves. So this is a graph that depicts these items. So there are some performance estimation method which are categorized into empirical, numerical, and experimental mode. So the purpose of these methods for empirical, it is for quick predictions in early stages design where you don't have access to any of these high fidelity facilities such as CFDs or experimental facilities. So some of these tools that are available in market or in open source, it's Savitsky, Blount Fox for the basic resistance prediction, and Ikeda and strip theories. So these models are for the sea-keeping predictions. So you can identify the frequencies, you can identify the RAOs through these models. And when you come to the numerical category, you will find out they are to identify a much detailed flow analysis and performance analysis, where you can see it mimics the real condition. Although there are limitations in the numerical models because the numerical models are not yet achieved the level in par with the real term conditions, because there are some discrepancies in turbulence models in also getting the vorticities, etc. So some of these examples are actually may not be able to get complete visualization patterns, but it at least gets 90-95% accurate patterns. So some of these tools, what we have is CFD based on RANS, or we have other CFD models such as DES, LES. They are very high fidelity models, and we have recently the smooth particle hydrodynamics also. And obviously, we have the experimental facility or the field test, which is a very real world conditions. It really mimics the real world conditions, which you can do it with the towing tank test or circulating water tunnels. Or if you have access to the sea, you can directly do this model test at the sea itself. And some of the key results of LORELEI projects, I'm just giving a simple simulation what we did in CFD. This is a planing hull form that was developed in-house at CMI under the framework of the LORELEI. So the boat will be optimized for its performance and shall be tested in the towing tank in future for validating the numerical results. So as we are gearing up for some publications, we will not be able to give more information about this. But nevertheless, we encourage you to regularly monitor our social media platform for quick updates on this. So having said this background and fundamentals of the vessel design and predictions, we'll focus on the specifics of the USV design challenges in the next section. So when you are designing any autonomous marine vessel, we have to go beyond the traditional design spiral, because the traditional design spiral doesn't account for any of these USV characteristics. It's not about the hull shape anymore. We also need to consider the new requirements of the USVs, like system reliabilities, safety, adaptability, autonomy, sensors, etc. This means we need to have continuous evaluation of the real world factors that might not fit the ideal design models which we traditionally use for the ship designs, to make sure the vessel performance is reliable in all conditions, in all operating conditions. Two key aspects we have to consider here, which is flexibility and robustness. So flexibility lets the design to adapt to the changing environment, loads, regulations, etc. While the robustness ensures consistent performance and structural strength, including the hydrodynamics also. So even under very wash conditions. So together, all these things will really help in a very greater design, which is very reliable, efficient, and easy to maintain throughout its lifetime. Having said this, having said this as an introduction, let's discuss a little bit more about this in detail in the coming slides. So now we see the design spiral is getting expanding in order to accommodate and integrate this onboard computing systems, sensors, AI systems, additional to this existing one. When you see it in terms of autonomy and control systems, the hull form and the integral layout need to be planned carefully to make sure that it accommodates the sensor, have a clear view of clear field view, and that all the electronic systems that are getting the proper cooling. The hull form and the integrated layout must accommodate so the proper cooling, and the stability and trim analysis must be done every now and then, because you are going to have a variety of components, and that should not affect your stability of the vessel. You need to consider both intact and damaged stability, and you also have to do a trim analysis, which becomes more complex because you have to account for the variable weights. So the sensors and the control modules may keep on changing over the period of time. So you have to take an account of that. And watertight integrity is very, very important that you have to consider. Communication and data link. The structural design need to be account for a few more important things. So I've given a picture of the vessel where the structural design itself is completely different than the unmanned vessel. First, you need to see the design for antennas, mounts, and protected compartments for all the communication hardwares. This ensures that the system is both secure as well as reliable, because there might be requirement for some water tightness even above water level because of this sensitive equipment. So you must consider the structural integrity of it. Since these autonomous vessels are consistently transmitting data and they have the sensors running 24/7, the power to the systems has to be sized as large as possible to handle that continuous load. Because if the vessel is not able to transfer the load continuously, then there is no point in having this USV for operation. So it has to be as large as possible, and it has to provide the data for a very long time. And finally, to ensure the reliability, we add redundancy in the network system. But also that makes the electrical and control layouts are very more complex. So that's very important. The electrical layout systems we have to consider, which was not previous concerns in the traditional design spirals. And in autonomous vessel design, the power and energy management becomes really important. That becomes a very early issue from starting of this design process. We have to look closely at the energy balance, since every system on board, from sensors to propulsions, depends on it. So we need to have a very good energy balance on board the hull form. Using this hybrid or renewable power systems that can change how we manage the weight distribution, how much the hull space is utilized, now how much of this hull space is available for the equipment and fuels. And finally, the thermal management and endurance optimization play a very big role in deciding what kind of propulsion system we are going to use. So we'll look into this in little bit more in a while. when we discuss about the propulsion systems. So finally, the power management is just not about the efficiency. It directly shapes the vessel's overall design and performance. So that's very important. When designing for payloads and mission flexibility, the hull geometry and the structure need to be able to support these modular designs. So the modular payload zones are to be identified and the areas that can be reconfigured depending on the missions. Since different payloads have different weights and different weight distributions, we also need to adapt the trim control to keep the vessel stable and properly balanced. And also we need to consider the vessel's water tightness. These variations directly influence the arrangement of the drawings, especially the general arrangement capacity plans of the vessel drawings. So flexibility in both structure and the design becomes essential for reliable operations. These are some key parameters we have to note down. And when it comes to the safety, reliability, and redundancy, these needs to be integrated in the early stage of the design spiral. That means including the fault tolerant systems and redundant propulsion systems from the starting point of the design. So whenever you start the design of the USV, you have to consider all these things into account. So these decisions will really affect the vessel's compartmentalization, internal layouts, general arrangements, weight distribution, stability, etc. So everything has to be accounted at the very, very early stages of design itself. So we cannot take these things for granted. If you make any mistakes here, then it's going to really affect the performance of the vessel, or the whole design process has to be repeated. On top of that, additional safety systems like self-righting mechanisms or fail-safe features can influence the hull geometry itself. So far, the key is to drive the overall design. So these are some of the very much important parameters that we have to take care. And finally, the regulation and operational impacts. So when it comes to the design of an autonomous vessel, compliance with LORELEI-X, so the International Convention for the Collision Avoidance Regulations, affects the control logic where we have to place the sensor. So some of these regulations has to be complied with when you design this autonomous vessels. And on the other operational requirements are like remote launching and recovery system that can influence the hull form design and appendage design as well. It is also a part of the projects. So we are also aiming to design one such structure on the vessel. And I'm sure that you'll be amazed to see that in future development. So certifications from the classification society, certifications from the flag state also play a very big role. It impacts the timeline, documentation, and decisions iterations. For example, recently I have come across that the Sail Drone Voyager is the first class of USV that was certified by ABS, and the Aqua Ocean Pioneer has been certified under the UKMCA, so and the Lloyd's Register. However, based on our experiences at CMMI, we are being part of several classification societies on several different projects. What we experience is at least 6 months to 1 year is a minimum requirement for any certification process. So you need to give this time frame for certification. So you also have to comply a lot of these regulations that are arising now and then. So because when you go and apply with these documents, you have to comply with their regulations. Each classification society, each flag states will have their own regulations. So at the beginning of your design phase itself, you have to decide that under which class or under which flag you will be registering your vessel. So this is very important. If you are not complying that at the beginning, then you will have to redo the design, redo the whole process. And that's going to affect every timeline of the fabrication work. So regulatory requirements are not just paperwork. You will not just submit the drawings, the documents, and the related items. They actively shape your design decisions. So that's very important. So with this, I'm sure that you would have got a very big global picture of the USB design requirements. So having said that, we'll move on to the next phase, which is the materials and modular hull forms. So you can see on the right side, we have our own CMMI vessel, FLIA Aphrodite, which was completely built with local resource at Cyprus. And this is a complete composite hull form. It's a battery propelled hull form. which has PVs on top of it, completely on the renewable source. So the modern USVs rely heavily on these advanced materials. So unlike the old traditional materials, they are not anymore in these USB designs. So we are mostly relying on the advanced materials like carbon fiber composite, Kelvar composites, or some of these alloys materials. So these materials give us high strength to weight ratio, high specific strength, which improves fuel efficiency, endurance, resistance, sea-keeping characteristics, corrosions in a very harsh and worse environmental conditions. Of course, these materials comes with trade-off. I'm not denying that. So they can be expensive. They can be very hard to manufacture and sometimes hard to repair also, and require very good and skilled manufacturing process. On top of that, the modular designs for the lets the USB to adapt for different mission by swapping these payloads, swapping the systems. This is very important because unlike the manned vessels, it's not easy for us to do these modular designs. But for USB, it's very easy when you design it in a very precise manner. But this flexibility introduces new challenges in terms of structural integrity, module interfaces, power distribution, etc. So these are some of the key points which I have want to discuss today. To make this modular USB work well, you need to ensure that the system's compatibility, watertightness, stability, integrity of the hull in structural form and software is all in proper form. In short, the modularity and advanced materials can greatly enhance the capability, but requires a very, very careful design at the beginning stage itself. So that is something I have to mention you in the beginning itself, so that we can discuss this in detail. So now the traditional vessels are made from steel, aluminum, and other alloys. So these materials are strong, of course, and they are reliable, but they are very, very heavy. So this steel, aluminum, or the alloys, they have a very, very low specific strength. Their densities are very high, and they also have some of these unusual the characteristics such as corrosions, which we can see a little bit later. So they are not anymore used in this maritime industries, and there is a need for advanced materials for these USB applications or for this high-speed applications. So the most modern USVs are increasingly using these advanced materials to take this advantage of these properties such as lightweight constructions, ease of maintenance. So composite materials are one such material, the synthetic composites, such as carbon fiber, glass fibers, not only reduces the weight, but also increases strength. They have enormous strength when you compare with the metallic counterparts. So this shift from the metals to composite helps the designers and also the owners to improve the endurance, the stealth technology, and operational efficiency, which is especially important for model maritime applications. And the table here depicts the key properties and typical application of the synthetic polymers that are largely used in today's USB design process due to their mechanical and chemical properties. So if you see that the carbon fiber has a very high stiffness, and they are typically used in this hull and structural panels. There are carbon fiber propellers that are being produced in these markets, and in terms of fiberglass is becoming more and more common in in the low size hull forms. For example, the hull forms that are up to 20 meters, 25 meters, carbon fibers are being preferred by the shipyard as well as the ship owners, because it has very low cost, easy to mold, good corrosion resistance. So these are some of the key advantage properties that these alternative material has compared to the metallic ones. And as you said, that the pros and cons, I've listed some of them for composites. So we have seen that it's lightweight, it's immune to salt water, it has excellent fatigue strength compared to the metals. It has a good stealth property that's very important for naval and defense applications. And the manufacturing could be a little bit complex, but now there are a lot of research that's going on in manufacturing, like additive manufacturing is getting up. So maybe in in near future, you can see the manufacturing process of composites also could be very, very easy. Of course, there is an initial higher cost, but when you see the OPEX, that is very, very low compared to the metals. So these are some key advantages and uh, better properties of these alternative materials when you compare with the conventional metals. And regarding the modular designs, so the modular designs lets the USV switch the mission payloads quickly and more efficiently, making them more versatile. These modules can include sensor packages, weapon systems, or scientific instruments, depending on whatever is the mission. When you design this modular system, it's crucial to ensure the mechanical compatibility, watertight integrity, and secure these connections for both power and data. So in short, if you see that the modularity gives you flexibility, but also requires careful engineering to make everything work seamlessly. So one must choose carefully before proceeding with the fabrication. Tolerance level should be extremely minimal. You are not afford to make any mistake here, and even to a millimeter level difference will really make things worse. So very highly uh, challenging process is being involved here when you want to go for this modular design. Of course, if you are successful at this, it lets you to use this vessel in a very different applications. So with that, we complete this second section. Okay, yeah. So there is a small advantage disadvantage missed. One must properly consider the cost benefit analysis and choose it accordingly. Yeah, that's what I said. So you must have to see whether your vessel to really design this modularity, or you're going to have them, or if you're having only one mission to accomplish by designing this hull form. So you are free to go only with a single design. But if you have to design a hull form that can be used for multiple applications, then you must consider this modular approach so that it's going to be really beneficial for you. It must be properly justified before you applying this design approach. Therefore, we must take use of this advantage of this modular design, and the advantage of this alternative materials for increasing the performance of these planing hulls wherever is possible. Yeah. Now we are into the fourth section. So we will now look at into the propulsion concepts. I'm sure everyone agrees that the propulsion unit is the heart of the vessel. Any wrong decision you make in the propulsion unit design is going to affect the vessel's performance. So the the modern USV are benefiting from the new propulsions, which enhances the efficiency, endurance, and stealth. Advanced concepts have emerged to further improve in terms of the maneuverability, in terms of seakeeping, stealth performance, supporting the push towards sustainable and autonomous maritime operations. And integrating this system into a compact USV hull can be still challenging because of the space, the constraints we have in the planing hull forms, and alignment issues. We have some stability concerns because of low volume areas we have in these compartments. Designers need to balance the hydrodynamic efficiency, structural strength, and vibration control to ensure the reliable performance across different missions. So let's discuss some of them in detail in upcoming slides. So when you see the conventional propulsion system, you have a diesel engine. The diesel engine will have a direct propeller shaft. This is a direct propeller shaft that drives directly the diesel engine, and you have a gearbox, conventional gearbox, and you have the thrust works again in order to get the thrust from the propeller, and you have a lot of bearings, shafts, flanges, a lot of rotating components that are being involved in this conventional propeller system that actually produces a lot of noise and vibration. This is a common problem in this diesel engine and mechanical systems. As they produce a lot of this noise, they are very harmful to the marine life. That's what recently we have identified from the Marine Environmental Protection Committee amendment. So we need to reduce the underwater noise as much as possible. So it's time for us to look for new and alternative type of propulsion units in order to have the reduced emission of underwater noise that is was suggested by the IMO. And it's also being advocated by a lot of these flag states. And some of them I've listed here. It may not be an exhaustive list, but some of the key propulsion technologies that are being used in the maritime industry. Some of the popular ones. The first one would be the electric and hybrid system. I have listed a figure here. So you have the diesel engine, and the diesel engine will generate the AC power, and that will be converted as a DC power by a power converter device. And this DC will be supplied to a motor, and the motor will drive the motor will have a drive shaft, and the drive shaft will drive the propeller. So in this way, it really makes the operation very much quieter. It emits low noise, and it has better efficiency also. And the next one is water jet propulsion. It has a very high level of maneuverability and really works well in shallow water, and it also helps you in achieving greater speed. So I have a cross section of the water jet propulsion system. So you have a duct, you have a driving shaft. Of course, this drive shaft could be either battery based or it could be also IC engine based, and it has a propeller fixed to the shaft. And there is a outlet duct. This duct could be made active so that this can help you in getting higher maneuverability as well. And through the nozzle, the water is being pushed out of this system. So that's how this water jet propulsion works. And very recently, we are getting more advanced concepts like rim-driven thrusters, which are compact. Yes, this is a rim-driven thruster. So it doesn't have the whole. Not only the propeller, the whole device rotates, and this are found to be more compact and low noise compared to the conventional device, and they are ideal for the stealth and survey operations for USVs. And similarly, you have the podded propulsion system that combines propulsion and steering in one unit, which simplifies the mechanical layout also. So those are also some of the advanced propulsion system. And finally, you have the magneto hydrodynamic propulsion, which is not at existence, but it has a very useful technology that is being developed. And what happens is this magneto hydrodynamic propulsion uses the electromagnetic force to push a conductive fluid like plasma or like salt water, which means the propulsion is done without moving parts. So if there are no moving parts, and it will not have any noise that is being produced, and it's a very, very futuristic approach. We don't have any prototype that's that's available in the market yet. It's in a very, very low TRL level, but it's a very, very good approach that we are doing it. So each of these technologies has its own disadvantages and advantages depending on the mission requirement and vessel design. So we need to carefully consider this. So some of them may be applicable to some applications and may not. So we need to choose them very carefully. Then next is hull propulsion integration challenges. So how are you going to integrate this propulsion system to this hull form? Because the traditional hull forms are basically designed for the conventional units, but you need to now modify the hull hull characteristics. The entire stern part of the hull should be modified in order to accommodate this novel new propulsion units. So when integration of the propulsion unit system, there are several key challenges that are being associated, which need to be kept in mind. The first is hydrodynamic compatibility. The propulsion unit has to match the hull flow characteristics. You need to consider the wake into account in order to avoid unnecessary additional drags. So the weight characteristics of the hull form should be taken when you are selecting these units for your primary propulsion system. And the second one is the space limitations are also important. Since the compact USV have a very little room for motors, batteries, and the cooling system, therefore it is challenging to accommodate without compromising the stability. And third one is structural constraint. So the structural constraint matters too much because mounting this thruster system affects both hull strength, because you may have to install a very different fixtures to avoid vibration of this motor when they are operating. So you need to have very modified engine beds or motor beds. So that might affect the strength characteristics of the vessel, as well as you need to consider the weight balance. And for electric drives, batteries, thermal management is very much critical. In order, you need to keep the system cooling in sealed compartments. Proper ventilation should be arranged without compromising the hull water treatment, because when you use these battery systems, you must give proper ventilation. Otherwise, there is a chance of getting it burnt, or it might be hazard. So you must provide proper ventilation system for cooling. However, it should not compromise your water tightness or structural integrity of the vessel. And finally, the system alignment must be very much precise. The poor integration can lead to vibration, noise, or reduced performance. So careful planning is essential to get optimized performance from these advanced propulsion systems. And finally, we are in the last section. Until now, we have seen some of these key challenges and state-of-the-art technologies that were used in the design and manufacturing of this USV. So as we are close to the end of this session, so we'll quickly see how these future trends and the topics related to AI, which are new technologies, are helping us and aiding this USV vessel design process. So we have seen that AI has tremendously intruded in day-to-day life and in maritime sector also. So let's see how it is helping the design process. So the artificial intelligence and advanced digital technologies are really changing how the design and predict the performance of the USVs by using these AI-driven simulations. So there are a lot of new AI-driven simulations have come with optimization algorithms and real-time analytics. So the designers can work much faster and more accurately in identifying this performance prediction and design process. These tools, sorry. These tools allow faster design iterations, enable predictive maintenance, and support the adaptive control system, which together improves the operational performance at sea. In short, AI helps USB smarter, and it makes more reliable and more efficient. So the next one is AI can also help us in understanding the requirement more clearly, and the optimization of hull form can be done in a more better manner than what we do it today. And the powering system could be much optimized, the battery management could be much optimized, and stability parameter also could be optimized. So these could be done through various methods, such as machine learning. As we know that CFDs the experiments are very costly tool and very difficult to access also. The AI could help us in framing this data-driven design to predict the hydrodynamic performance. So that is one greater advantage we foresee. So, generative design and optimization algorithms allow us to choose from a variety of alternatives rather than the standard designs. So we can use new AI technologies on that. In addition, the CFD codes, whatever we have now, could be automized completely with AI models in order to predict the performance of the hull forms. The AI has different models, such as AI-based surrogate models can be used. They are DNN, the deep neural networks, artificial neural networks method that reduces our time frame. And we can also simulate a variety of conditions via digital twinning of these models to mimic the real world conditions. It helps really in identifying the life cycle of the product and enabling us to monitor the performance in real time. And with AI, you can also make the boat completely autonomous. It enables for better navigation, obstacle avoidance, route optimization, etc. So reinforcement learning algorithms allow USV to adapt to change environmental condition with appropriate decision making, which could be achieved by giving proper training to the models. And real-time sensor fusion and decision-making system improve the mission reliability and safety aspect. So the AI algorithm can analyze the sensor data to predict the mechanical failures before what they happen. So which helps us to really improve the reliability and reduce the downtime. When you integrate this AI models with IoT and cloud system, the USVs can support remote diagnosis. So you need not go to the place where the USV is having this fault. So you can do it from a very remote location. And even software updates could be done at the sea itself. So that is very, very advantageous for us. And looking ahead, the future points towards combining AI, robotics, and the smart materials to create a fully autonomous, energy efficient maritime systems. And in short, AI is not just about smarter control, it's about transforming the entire life cycle and capabilities of the USVs. And this will be the summary or conclude slide. And today we see that the USVs are challenging to design and demonstrate. And hydrodynamic must be integrated with controls. That's very, very important. Modular designs are more preferable and it allows more flexibility also, and use it wisely whenever it is required. Then we have identified there are novel propulsion systems that are available for these USV designs. And finally, an appropriate use of AI leads to greater performance. And with that, I would like to conclude my presentation. And please do support us on our social media platforms and be watched for the latest updates about the LORELEI project. Thank you.
Thank you, Ashok. We have a question from the audience. So maybe, I think this question is for you, Ashok.
Yeah.
Can you explain the importance of a vessel's fuel capacity and therefore its endurance when designing a planning vessel, particularly when the vessel is small, because the center of the gravity will change with time?
Yeah, I agree with that. So, whenever you plan vessel design, so three key aspects has to be kept in mind. The one is speed, specs. The second one would be the cargo, and the third one would be the endurance. So when you identify the endurance of the vessel at the very beginning stage, so you will be able to identify the fuel that is required for the whole travel. And how you can do it in the USV is you can make small compartments. So for large vessels, you have large tanks, but in USV, in order to maintain the stability and dynamic trim, you must have to have larger compartmentations. You must have small compartments across the hull form, and from there you have to take the fuel into your propulsion system. You must have to do a large compartmentation process. I hope that satisfies. Yeah.
Hopefully that will answer the question. I have a short question for Nikos.
Yeah.
Are you able to? Yeah, thank you, Nikos. So thank you for the presentation. So for myself, I'm interested in route planning. So you said that in one of the points in your presentation is that we can integrate the maneuvering models into a real-time decision making or route planning. So can you give some insight about how the increased model complexity will affect the computational load during the optimization?
Yes, so I'm not in this field, actually, in the autonomous vessels field. So I don't know much about this, but well, as I showed with the last example, you can figure out simple constraints like not integrating the whole maneuvering model onto the route planning algorithm, but maybe using the maneuvering model to represent the the maneuverability of the vessel through some constraints. For example, the vessel has a limited yaw rate. It cannot have an infinite yaw rate, or its stopping time. We can relate the accelerations, for example, of a vessel with simple constraints. Yes, and also further constraints can be added when the ship is operating in waves, for example, or in large wind. Then we can enforce stricter constraints, and we can figure out what these constraints should be from the maneuvering model. I don't know how we could integrate it into the path planning model. Maybe you would know that better.
Yeah, thank you. I think we can discuss a bit more in detail later.
Yeah.
Because I think we have 2 more minutes for the webinar. I don't see more questions popping up. So maybe I think it's time for closing. Thank you everyone for joining today's webinar and for the discussion at the end. So on behalf of LORELEI-X Consortium, I would like to thank 2 speakers today to share their expertise on vessel design and maneuverability modeling. So this is very valuable as we work together towards a smarter and more autonomous marine system. So this was just the first series of the knowledge exchange activities within LORELEI-X project. So we encourage you to stay connected, follow our project on the website, LORELEI-X project.eu. And then you can reach out to us if you have any questions or any discussion that you want to take up. Thank you for your participation, and we look forward to the next event.